Hi and welcome to this Leaving Cert higher level video where we're going to look about solving inequalities. Equalities will act like equations, except instead of an equals, we see them having an inequality sign like less than or equal to, greater than or equal to. As part of this video, what we're going to look at is solving quadratic inequalities, rational inequalities, modulus equations and graphs, and then modulus inequalities, and also looking at how to bring in the discriminant into these type of questions. I'm not going to look at any linear inequalities as these are rarely asked on the higher level course. So let's just do a little bit of background on inequalities before we start. My method that I like to use for all these questions takes into consideration that equations and inequalities will act in exactly the same way except in one case. So let's take an example of 2 less than 3. So because I'm saying it acts like an equation, we should be able to do the same thing to both sides and it stays true. So if I add a 3 to both sides, I get 5 is less than 6. And is that correct? Yeah, 5 is less than 6. What if we subtracted 2? So is 3 less than 4? And yeah, that's also true. Multiply by 4, so we have 12 is less than 16. Again, yeah, that's perfect. And what about division? So 6 is less than 8. So adding to both sides is no issue. Subtraction, multiplication, division. So it's acting like an equation. We just need to ensure we keep that balance. We do the same thing to both sides. There is one time where an inequality will not act like an equation, and this comes about where we talk about a change of sign. So in an equation, if minus x equals minus 3, we'd simply say, well, then x equals 3. We can think of this as multiplying or dividing by a -1. However, it's easier just to think we change signs on both sides of the equation. Now, when that's true, when we have the same idea happening in an inequality, that's where the problem kicks in. So for example, I have 6 is less than 8, but is minus 6 less than minus 8? And it's not. So minus 6 is actually bigger than minus 8. So that's incorrect. So what we're going to do instead is, if we need to change the signs, which again, based off a lot of the questions, it'll be so much easier if we can. If we change the signs, a quick fix is to change then the inequality sign. So we flip it. So what I like to do in any of these questions is make a little note that when we change the signs, we change the inequality sign. Now, depending on how you've been taught this and how you've learned this, you may talk about multiplication and division of negative numbers. That is what will cause a change of sign. I find that's a little bit confusing, and students can often then change the inequality sign when they shouldn't, because in their head they think multiplication and division. So an easier way, in my opinion, is really to focus on, if you need to change the signs, change them, change the inequality sign, and then go about your multiplication and division separately. Let's look at a quadratic inequality. I'm going to put some steps up here. There's a few different ways to approach this, especially for step 4. I like this step 4. I think although it's drawing, it is the easiest and quickest, and it links in so easily to everything that you should be able to do. But if it feels unfamiliar to you, there are other methods out there. So solve the following quadratic inequality. So x squared minus x minus 6 is greater than or equal to 0. So my step 1 is I ensure that I have a positive inequality. Now there's 2 reasons for that. One, it gives us consistency in these questions. It means that drawing will always be a positive inequality, and it's one less thing to think about. The second reason I strongly encourage it is because if we want to then solve the corresponding equation and use factorization, which we'll do in pretty much all questions, you're going to want to work with a positive equation. So why change the equation step and not change the inequality? To me, that doesn't make any sense. So if I don't have a positive quadratic inequality, I change it. Here, I do have a positive inequality, so I'm going to leave it. Now, step 2, and this is an important step because early on they did state that they didn't give full marks if this step wasn't shown. I think regardless, it's so important to understand that we're not solving the inequality. What we're going to do is we're going to solve the corresponding equation and use our answers to figure out the answer for the inequality. So it's a very subtle difference. I find that students can often just randomly try guess the inequality signs at the end, which isn't good. So I find converting to an equation and doing so explicitly is so important. So I have the equation x squared minus x minus 6 equals 0. I'm now going to solve that equation. So in order to solve the equation, you have two options. We have factorization or you've minus b. Again, minus b, you can always use it, but it's going to be excessive in this case. So sometimes in the mock exams, we might see equations that with big numbers, and it might be easier to use guide number, or it might be easier to use minus b. But in the whole, for what we've seen on the actual paper, factorization should be sufficient. I'm going to use shortcut of guide number, which means I'll get my guide number, which is minus 6. And then I'll find its factors that add to minus 1, which is minus 3 plus 2, and just place it in our bracket. So that gives me x equals 3 and x equals minus 2. And that's my answer for the equation. It's not my final answer for the whole question because the question asked me an inequality. So my answer should then be an inequality. Now what I'm going to do is for my step 4, and again, you may do this slightly differently, I'm going to sketch my inequality. So I have a positive quadratic, so it looks like this. Try to really open that up. Sometimes students do it quite narrow and the arms point straight up. They should point out. So it is only a sketch, so as long as I put in my 2 roots, that's absolutely perfect. So they're the roots that I got from my step 3. Now I'm going to go back to my last inequality. In this question, I just had the inequality. So it's greater than or equal to 0. And I have this quadratic greater than or equal to 0. Or another way to think about it is the graph is greater than or equal to 0. Or the function or y is greater than or equal to 0. So when we talk about greater than or equal to 0, what we mean is above the x-axis. So we're looking at where is the graph above the x-axis. So using a highlighter, I'm going to show you the 2 places where that happens. So above the x-axis. The corresponding x values lie along the line here and along the line here. And that allows us then to get our final 2 answers, which is that x is bigger than or equal to 3 because it's moving to the right. Or on the other side, x is smaller than, less than or equal to minus 2. Because the question had an or equal to in it, I'm going to have an or equal to in my answer. Another thing to note is I have 2 distinct or different pieces highlighted on my graph. So my answer should therefore be 2 distinct pieces. So x is less than or equal to minus 2 and x is greater than or equal to 3. Let's look at a second example. I'll move a little bit quicker here. Solve the following quadratic inequality. So now we have a negative quadratic inequality here. How we know it's negative is because the sign on the x squared is negative. How we fix that is we are going to change the signs. If we change the sign, so we'll have x squared plus x minus 6, it's important that we also change the inequality sign. So the inequality becomes x squared plus x minus 6 is less than 0. So now we're going to convert to an equation. So that equals 0, and we're going to solve that. We get x plus 3 times x minus 2 equals 0, and that is x equals minus 3 and x equals 2. Step 4, we're going to sketch this out. Our two roots are negative 3 and positive 2. This is the last inequality that we had. So I'm going to go back to the last inequality, which is this one here. Okay, so as these inequalities get a little bit more complicated and there's more steps to lead up to that, I find highlighting it in some way makes it easier to find what we are using for step 4. We have a less than 0 here, which means we're talking about below the x-axis. Now, below the x-axis is one piece and it sits in this loop here. The corresponding x values sit between minus 3 and 2. Now, how we can write that is the minus 3 goes first, it's the smallest, the x sits in the middle, and the 2 goes out here. So the x is between the minus 3 and the 2. I always think it's easier to look at the higher value and to think the blue line x is less than 2, and these signs will always match, so they'll always point the same direction. So my answer is minus 3 is less than x is less than 2. Just be really careful to answer the question. The question was a greater than sign. There was no equals. Therefore, in my answer, there's going to be no equals. Let's try another one here. Solve the following quadratic inequality. Just like solving quadratic equations, it's important that the right-hand side is equal to 0. So the first thing I'm going to do is I'm going to bring everything over to one side, so that's minus 15 is greater than 0, and ensure I have a positive quadratic. I do. Next step, I'm going to make this into the corresponding equation so I can solve it. So this is what we're going to solve. Now, we're going to use factorization here, but in this case, and I'm thinking if you're using like guide number, the number is quite big. So 6 by 15, so that's 90. So you might struggle with that a little bit, 9 by 10, but if you were, you could use minus b here. Whatever way you approach it with factorization, this should be your final answer. So now we're going to let each of my brackets, each of those factors equal 0. So x is equal to 5 over 3. 2x equals 3. So x is equal to 3 over 2. Now it may help, sorry, that should be a minus 3 and a minus 3 over 2. It might help if you're plotting to put these as fractions, or sorry, rather put these as decimals. It's completely up to you. So now I'm going to do a little bit of a sketch. My sketch is going to be for the last quadratic, which is x squared minus x minus 15 is greater than 0. My greater than 0 means I'm above the x-axis. So I'm going to draw this out. I have two roots. One is positive, one is negative. So I have 5 over 3 here. I have minus 3 over 2 here. I'm talking about above the x-axis, so here and here. Those corresponding x values represented on the number line here and here. So that is x is greater than 5 over 3 and x is less than minus 3 over 2. Remembering again that we do not have an equals in this question, so there is no equals in our answer. So let's now look at working with discriminants. you may be limited with how much you can do with discriminants if you learn about discriminants before you learn about inequalities. So the discriminant is the part of the minus b formula which tells us about the nature of the roots. So are the roots real? Are they real and distinct? Are they real and equal? Or are they not real, or rather imaginary? So this question asks us to find the range of values. So the range implies that there's going to be an inequality sign. So the range of values of k for which the equation kx squared plus 4x plus 3 plus k equals 0 has real roots. Okay, so first thing I'm going to do, this is my quadratic and I want real roots. So my discriminant is b squared minus 4ac. You need to know that. It does come from the minus b formula. It's what's underneath the square root. That's the piece that changes the nature of the roots. So the first thing then I'm going to do is underneath my quadratic I was given, I'm going to label it like we would label a quadratic to use the minus b formula. And that is ax squared plus bx plus c. Now, this is a tricky one because c is the constant, and maybe up to kind of third year you felt the constant was the number, not the letter. However, there is a difference between the letter used for a constant and a letter used for a variable. So an easy way to think of a constant in the case of a quadratic is it's the non-x term. So anything that doesn't have an x attached. So that will be in this case 3 plus k. And that should equal 0, which it does, so we're on the right track. So now our discriminant, b squared, so I'm going to write down my a, so is k, my b is 4, and my c is 3 plus k. I have real roots, so what that means is b squared minus 4ac will be greater than or equal to 0. That's how I know that I have real roots. It didn't say real and different, it didn't say real and equal, so I'm combining both of those to have a greater than or equal to 0. So this is 4 squared minus 4 times k times 3 plus k is greater than or equal to 0. That is 16 minus 12k minus 4k squared greater than or equal to 0. I have now a quadratic where we're working with k. I want to make sure I have a positive quadratic, so I'm going to change my signs. So it's plus 12k minus 16 is less than or equal to 0. It's also got a common factor of 4, so I'm going to divide across by 4. This simplifies it. You'll still get the same answer if you don't, but it'll be a little bit harder to work with. Think about having to factorize the previous line compared to factorizing the last line. Now that I have my quadratic inequality, I instead solve the corresponding equation, which is k and k, so minus 4. So I'm going to have a plus 4 in one bracket and minus 1 in the other. That gives us 2 factors and corresponding to roots. K is minus 4 and k is 1. Now I'm going to do a little sketch, and it does just need to be a small sketch. I'm going to be working with this quadratic. That's the last quadratic inequality I have. I'm going to make a little note here because I'm short on space. It is less than or equal to 0, so we're talking about below. So my sketch will look like this. My minus 4 here. 1, you might say, oh, that doesn't look like it's minus 4 and 1. That's fine. It is only a sketch. It's only to give us a sense of where we're looking on the graph. So less than 0, so we're looking below this portion here. That corresponds to the x values in here. Remember, when we're dealing with this one section, we'll get one combined answer. X is in the middle. It's between minus 4 and 1. Focus on one side. I find it's easier to work with the bigger side. So it's going to be, oh, I might put an X in there, but we're dealing with K. So it's going to be the blue part, the K is less than or equal to 1. And then remember, the second inequality sign will match the first. So once you figure out one side, the other will follow. If it's always a positive quadratic, they will always be less than or equal to signs. Let's do a little bit more work with discriminants. Let f of x equal x squared minus t plus 2x plus t plus 2, where t is a constant. Find the range of values of t, element of real, so t is a real number, for which f of x is represented by the following graphs. So we have three scenarios here. In graph A, there are no real roots, so they're imaginary. In graph B, there is one real root, or rather real and equal roots. And in C, they're real and different. So this is the discriminant, and it's going to be negative. So that's the bit under the square root. So what that happens if we try to solve that is we get error, because it's a square root of a negative number. It's equal 0 to give us this one root here, and for two roots we get this discriminant b squared minus 4ac is greater than 0. Now, since we're working with the discriminant in each, let's work with the discriminant first, simplify it as much as we can, and then see how we can proceed with the three graphs that we've been given. So I am going to, underneath the quadratic, ax squared plus bx plus c. It's quite a complicated little equation or function. A is straightforward, it's 1, but b is minus t plus 2, and c is t plus c. So the discriminant, which is b squared, so that's minus t plus 2 squared minus 4 times a times c. And I want to clean that up. Now, a lot of students would actually, for b, multiply in that negative minus t minus 2 and then square it. That's perfect. However, if I'm squaring a negative number, it's the same as if I'm squaring a positive number, because any real number squared is positive. So if I had 3 squared, it's the same as minus 3 squared. So how that helps us is, if I want to square out this, it's the same as t plus 2 squared. I'm going to use my shortcut, which is square the first plus double the first by the second, that's plus 4t, plus square the last, minus 4t minus 4. I put a c in there, apologies, that should be a 2. So plus 2, so that is minus 4 by 2, which is then minus 8. I'm going to tidy this up a little bit more. 4t and minus 4t, they cancel, and we're left with t squared. I have a 4 and a minus 8, that gives me minus 4. So I have now t squared minus 4 is less than 0. T squared minus 4 equals 0, and t squared minus 4 is greater than 0. So there are my three scenarios. Now just be careful, although they're not quadratic trinomials, they are quadratic because there is a t squared, so that we need to treat them like we would treat any other inequality. So the first step that we would do when we have our positive quadratic inequality is to let it equal 0. So create an equation rather than the inequality and solve that. But graph B is the equation. I'm going to use difference of two squares here. I prefer difference of two squares than bringing the 4 across the equals, because I find in that case students lose one of the values. So here we get t equals 2 and t equals minus 2. So that's my answers. They are my answers for graph B. Now, for graph A and graph C, we're going to use those and we're going to find the correct inequality answers. So for both of them, they'll need a sketch. So let me clear some room here and we'll do a sketch of the quadratic with those two roots. So I have a positive quadratic. So here's my sketch. One of the roots is 2 and one of the roots is -2. So here we go. So there's my -2 and my 2. So let's look at graph A first. We're looking less than 0. Less than 0, which means below. So we're looking at this portion of the graph here, which corresponds to these x values. So those x values, t values, they're going to be between -2 and 2. The blue line is less than 2. So it is -2 is less than t is less than 2. Now, if we get rid of those highlights, you can do a second sketch. But I'm going to get rid of those highlights. And instead, now I'm going to look at graph C. So greater than 0, which means above. On the graph, that means these sections here. Those corresponding x values are here. So my answer will be t is greater than 2 and t is less than -2. So there's quite a substantial piece of work in this question. However, if you're clever about how you approach it, i.e. working with graph B first, if you have a good understanding of how to work with quadratic inequalities, it can be a much quicker question. I have seen students work on this question where they do A, B, and C out in full. It does take a little bit longer, and remember there is an element of time pressure in the exam. Let's talk about rational inequalities. So rational inequalities are inequalities that contain fractions. Remember your rational numbers. These are any numbers that can be written as fractions. When we have any fractions in an equation, we get rid of them by multiplying across by the common denominator. So like for this, we would do x by 3 and here x by 3. And this is what I see quite a lot with students. And I suppose it's the obvious choice, but it's incorrect. And the reason it's incorrect is because is x positive or is it negative? And the answer is we don't know. And because we don't know, we can't just multiply it. And the reason we can't multiply it is, let's take an example. If x was negative and we multiplied both sides by a negative number, what we will do is we will end up changing its sign. And by changing its sign, we will need to change the inequality sign. So instead of a greater than sign here, it should be a less than sign. But if you then say, well, okay, let's pretend x is negative, then we change the inequality sign. But what if it's positive? So then you've changed the sign incorrectly. So we run into an issue of we don't know. And because of the fact we don't know about this denominator, we need to be a little bit cleverer about it. So what we're going to do, and I'm going to get rid of this in case anyone thinks it is correct, is we're going to instead work with the square of the denominator. So instead of x, I'm going to multiply it by x squared, but I'm not going to square the 3. Now, the reason I square the x, but I don't square the 3 is because x could be positive, it could be negative, I don't know. But when I square any real number, it will end up being positive. So if x was like, say, -3, squaring it makes it 9. It's now a positive number and it's not going to affect the inequality sign. 3, on the other hand, is a positive number. I'm not confused about that. I know that it is positive and it's not going to affect my inequality. So when we're dealing with these rational inequalities, it's really, really important to remember that if we have unknowns, they are unknown, so we don't know if they are positive or negative. So we need to multiply by the square of those denominators. Example 6, rational inequality example. So here we have a rational inequality that is 2x minus 5 over x minus 3 is less than or equal to 5 over 2. So 2x minus 5 over, I like writing these out again to get a bit of space, minus 3 is less than or equal to 5 over 2. Now, to get rid of x minus 3, we can't just multiply by x minus 3. We need to multiply by x minus 3 squared. That way we know whatever x minus 3 is, squaring it makes it positive. Remember to keep the balance, so it still needs to be squared on both sides. I also want to get rid of the 2, so I'm going to multiply both sides by 2. I'll throw the 2 over here. I then can cancel the x minus 3 by the squared and the 2 by the 2 here. And now we can multiply out. So we have x minus 3 by 2x minus 5 by 2 is less than or equal to 5 times x minus 3 squared. Now, when we multiply this out, we're going to end up with a quadratic inequality. So if you struggle to remember the trick as it is, that squaring in the denominator, try and remember that if you don't get a quadratic inequality, you've done something wrong, and go back to it. So if this is very, very straightforward and very simple, and you get a very nice little answer, then you've done it wrong. It's meant to be an expansion to a quadratic, and then we'll apply all the steps we've already looked at for finding the answer to a quadratic inequality. So I'm going to multiply the 2 in. I'm going to multiply it by the first bracket, 2x minus 6, 2x minus 5, less than or equal to, I'm going to square this, x squared minus 6x plus 9. Split my bracket here, 2x by 2x minus 5 minus 6 by 2x minus 5 less than or equal to 5x squared minus 30x plus 45. I get 4x squared minus 10x minus 12x plus 30 is less than or equal to 5x squared minus 30x plus 45. It is a quadratic, so I'm going to bring everything to one side. So I have 4x squared, take away the 5x squared from the other side. Cleaning up the x's here, I have minus 10x minus 12x, which is minus 22x. I then bring over plus 30x from both sides, so I'm adding 30 to both sides. I have plus 30 and I take away 45, it's less than or equal to 0. So we're aiming for that right hand side equal to 0. We get x squared plus 8x minus 15 is less than or equal to 0. Now, I don't work with negative quadratics, so let's change it to a positive quadratic. So that is, change your signs, and when we change the sign, that will flip the inequality sign. So the quadratic inequality that we're solving is x squared minus 8x plus 15 is greater than or equal to 0. Now, some students, just to mention here at this point here, would say, well, 5 is bigger than 4, so I brought everything to the right. Now, in an equation, I'd say, yeah, that's fine. But in an inequality, I just issue a word of warning about then the inequality will be in front of it. So you need to still flip it to bring it to the other side. So to me, you're not really saving anything, and you could be more prone to error with that method. So I would always say bring everything to the left, and then if you need to change the signs, you can. And now we're back to a quadratic inequality question. We haven't ever really seen any quadratic inequalities come up. Instead, we see them asked as rational inequalities and modulus inequalities, because there's a lot of background work then that needs to happen. So as part of this question, in an exam, they've already tested, do you know how to get rid of the fraction in an inequality? Do you know how to square? Do you know how to multiply? Do you know how to simplify? So they're testing a lot of things. So from an examiner's point of view, it's a much better question to ask than simply, find the range of values for x where this is true. So let's go back to our quadratic inequalities. First thing I'm going to do is I'm going to solve the corresponding equation. So then this is x minus 5, x minus 3 equals 0. That gives me x equals 5 and x equals 3. We're going to do a sketch. It's a positive quadratic. And it looks like, oh, no, it doesn't look like this. So it doesn't have to be perfect, but we do have two positive roots. So I'm going to show it as two positive roots. We are looking at the inequality that is x squared minus 8x plus 15 is greater than or equal to 0. That greater than or equal to 0 means that we are above. So we are dealing with above the x-axis. There's my 5 and my 3. Getting my highlighter, I'm dealing with these two sections of the graph. They correspond to these two sections on the x-axis. And these are x is greater than or equal to 5. And x is less than or equal to 3. Now, that's our final answer. However, there is one other thing that you need to be aware of when we're dealing with rational inequalities, and that is that there will be a value that x cannot be. And in this question, it doesn't state it, but in an exam situation, they will give you something like x cannot equal 3. And the reason x cannot equal 3 is because if we look at the denominator, if x was 3, that denominator would be 0. And it's not possible to have a denominator of 0 because we cannot divide by 0. It's not possible to divide by 0. So how does that affect my answer? Well, here I have a less than or equal to sign because my question had an or equal to. However, since it cannot be equal to 3, we are going to instead just leave this as a less than 3. What I would say is, in an exam situation, if you see something like this, note that it doesn't affect this step. Sometimes I see students say, well, that route is not valid. It is a valid route for this quadratic equation. It is a valid route. It's not a valid answer for my final answer, but we're not at the final answer stage yet. So don't look at these until the very end of the question. So my final answer, zers plural, it's x is less than 3 and x is greater than or equal to 5. Remember, two distinct pieces on the graph mean two distinct answers. Let's talk a little bit about modulus or absolute value. So absolute value is a measure of how far a number is from 0. So 6 is 6 units away from 0, but minus 6 is also 6 units away from 0. So the absolute value of 6 is the same as the absolute value of minus 6, which is 6. So absolute value is another way to say modulus. I use the words interchangeably. How it's written are these two straight lines. Now you will have already met those two straight lines in a few places. You will have met them at junior cert when we were dealing with size. So the size of an angle, the size of a line, which really was length of a line, the distance formula in coordinate geometry, anywhere where we would ensure that we had a positive answer, because it wouldn't make sense to have a negative angle size. It wouldn't make sense to have a negative length. It wouldn't make sense to have negative area. So we often see it in those places. So there are two straight lines, and when we see them on either side of a number, it forces the number to be positive. So if the number is negative, like minus 5, the answer will be 5. So the absolute value or the modulus of minus 5 is 5. If the number is already positive, so the absolute value of 7 or the modulus of 7, it is the same. So it is 7. So it's not a change of sign. It forces it to be positive. So graphing them. So here are two graphs. So if y is equal to 2x minus 3, that is linear. It's a linear equation. Y equals mx plus c. If you've worked with that, m represents the slope, c represents the y-intercept. So that is a line that has a slope of 2 and crosses the y-axis at minus 3. Now, how would we change the drawing if we put modulus or absolute value signs on the 2x minus 3? Well, what we're saying is y then cannot be negative. So what happens is, and I'm seeing this backwards, I'll go along it. This part of the line is fine, but when it hits here, it's reflected, and that's a really good word. It is reflected back. So instead of being minus 1, it shows as 1. Instead of being, what have I got, minus 3 here, it shows as 3. Instead of being 2, it shows, negative 2, it shows as 2. So it's reflecting up, and we get this really distinct V-shaped graph. So it's not a curve, it's not like a quadratic, it is a V shape. And we would have, if we talk angles, this angle here would match this angle here. Now let's solve a modulus equation. So we're told that the modulus or absolute value of 5 minus 2x is equal to 11. So we have 5 minus 2x, and I suppose the issue we have is we don't know whether that's positive or whether that's negative. So to fix that, we're going to use a little trick, and that is squaring both sides. Now, why I'm going to square both sides is because when I square the left-hand side, I'll know for sure that it's a positive answer. At the moment, maybe it's positive, maybe it's negative, we're not sure. So we're going to square this out, and it is important that you square it. It's not like something cancels. You do need to square it. So we square 5, then twice. So we'll do 5 by minus 2x minus 10x and double it, minus 20x. Square the last plus 4x squared equals 121. We now have a quadratic equation that we want to solve, so we're going to bring everything to the left-hand side, which means I have a plus 25 minus 121, which gives us minus 96 equals 0. And there is definitely a common factor here of 4. You don't need to simplify it, but remember, factorizing will be so much easier if you do. So this gives me 24. So now the factors of 24 will give me 5, 3 and 8, so plus 3 and a minus 8. So my answers are x could have been minus 3 and x could have been 8. If you go back to our original question, when we sub in minus 3, we will have made it positive. When we sub in x is equal to 8, we'll get so minus 2, minus 16, so it would have been a minus 11, which was then changed to a positive 11. So let's do the same equation, but this time using a shortcut. So because of these absolute value or modulus signs, we know that 5 minus 2x is either going to be 11 or negative 11. So simply we can say, well, maybe 5 minus 2x was positive and it was 11. The second option is, well, maybe it was negative and we changed it to a positive. So that would mean it actually equals minus 11. Now we have two little linear equations that we can really easily solve. So we take away a 5 from both sides, which gives us 6. And one of our answers is x equals minus 3. We again take away 5 from both sides. It's minus 16. So we get x equals 8. So our two answers, same as our previous answer, is x equals minus 3 and x equals 8. So let's look at a modulus equation example. I'm going to approach this example in two different ways, and the first way will be using our longer method for solving modulus equations. So they've asked us to find the value of m for which the absolute value of 2x minus 3 is equal to mx plus 1 has only one solution. So what we're going to do is we're going to take the equation that we have, 2x minus 3, is equal to mx plus 1. And because we don't know whether the 2x minus 3 was positive or negative, we're going to square both sides. So remember, when you square an absolute value or modulus sign, you need to actually square it. Nothing cancels out. So we get 4x squared minus 12x plus 9 equals, now just be very careful here, squaring the first is m squared x squared. Remember, the squared only affects what it's touching, so mx squared just means the x is squared, but we have mx by mx, so the m is also squared, plus 2mx plus 1. So now what I have is a quadratic, and I want to bring everything to the left-hand side. So I have 4x squared minus m squared x squared minus 12x minus 2mx plus 9, take away 1, it's plus 8 equals 0. Now we can leave it like this, but I think it will be much easier if we can pull out the x squared, okay? So that will create a single x squared term, and that will leave 4 minus m squared as that coefficient of x squared. Let's do the same for x. That will leave me minus 12 minus 2m, and then a plus 8 equals 0. Because we've only got one solution, we're basically saying there'll only be one answer to this quadratic. So the easiest way to work with that is discriminant. And we're saying that the discriminant, b squared minus 4ac, will show that it only has one solution, so it will be equal to 0. So I'm going to write this as my quadratic ax squared plus bx plus c equals 0. That gives us a is equal to 4 minus m squared, b is equal to minus 12 minus 2m, and c equals 8. So the discriminant of b squared, so minus 12 minus 2m squared, minus 4 times a times c equals 0, and then we're going to solve for m. So let's expand these brackets and tidy up. So we get minus 12 squared is positive 144. Minus 12 by minus 2m gives us plus 24m, and then we double it, so plus 48m, and then square the last, plus 4m squared. To make this second piece a little bit easier, I'm going to multiply the 4 by the 8, so I get minus, the minus stays there, and then 32 by 4 minus m squared equals 0. So that's 144 plus 48m plus 4m squared minus, now so we have 32 by 4, and that gives us 128, so we get minus 128 here, 128, and then minus 32 by minus m squared gives us a plus 32m squared equals 0. We're going to tidy that up, and then we're going to solve it. So I'm going to just take my highlighter. We're going to add the m squareds. We're then going to add the constants, so minus 128 and L144, and then there's only one m term. So I'm just going to put it up here for the moment. So we get 36m squared plus 48m, and then that gives us a plus 16 equals 0. There is a common factor here, and 36, so we're going to divide across by 4. What that will do is just make it a little bit easier to work with. So that's divide by 4, and that leaves us with 9m squared plus 12m plus 4 equals 0. And we actually have here, because Now, here we have find the value of m. So we're only going to get one value for m. We have a quadratic trinomial here, and you can work this through using guide number or trial and error, whatever way you usually factorize a quadratic. However, because we're only looking for a single value, it's possible that this is a perfect square. So this could be 3m plus 2 squared equals 0. Now where I got that is I square rooted the 9m squared, I square rooted the 4, and then I just double check the middle term. 3m by 2 is 6m, and double it, I got 12m. So actually that is a perfect square. If you didn't want to do it, you would still get 3m plus 2 by 3m plus 2. You'll get the same answer if you do normal factorization. I now know that 3m plus 2 equals 0, so m is equal to minus 2 over 3. So let's look at another method for this. This method is going to use the shortcut for solving modulus equations. So I can say, well, if 2x minus 3 was positive, then it's just equal to mx plus 1. And then the second option, well, maybe 2x minus 3 was negative, so it was actually equal to, and now we change the signs. So it's minus mx minus 1. Now, the problem with doing this is you have to be really, really clear on what we're trying to find. So find the value of m for which this whole thing only has one solution. So what we're going to do is we're going to get an answer for x in terms of m. So I'm going to bring over my mx, and I'm going to bring over to the other side my 3, and then I'm going to isolate the x term. So it's using highest common factor, and I get 2 minus m is equal to 4. I'm then going to divide both sides by 2 minus m, and I'm left with x equals 4 over 2 minus m. I'm going to do the same thing for my second equation. I get 2x plus mx equals minus 1 plus 3. Again, I'm going to pull out that x. I get 2 plus m is equal to 2. I divide both sides by 2 plus m. This leaves me with x equals 2 over 2 plus m. Now, we know that this equation only has one solution, but we have got two solutions. So therefore, if there's only one solution, both of our solutions must give the same answer. So one solution. So this means, therefore, 4 over 2 minus m must be the same as 2 over 2 plus m. So we need to solve this equation for m. Now, anytime I work with fractions, especially when the unknown is in the denominator, I like to flip them. So if I know two fractions are equal, I know that their reciprocals are also equal. So what I mean by that is when we flip them, the value, although it changes, remains one side equal to the other side. This is just a little bit easier and quicker to work with. Now, to get rid of my fraction, I'm going to multiply both sides by 4. Some students might talk about cross multiplying here. I'm not a fan of the wording of that. It's used in the wrong place, so I like to think of it as multiplying by the denominators, or if there's the denominator, or if there's multiple denominators, the lowest common denominator. So now I have a nice little linear equation I'm going to solve. So I have minus m minus 2m. I like bringing everything to the left. 4 minus 2 minus 3m is equal to 2. So m is equal to minus 2 over 3. So the same answer as we got before. A quicker, more efficient method, but I think this is one that students would struggle to understand or at least come up with on their own in an exam style or an exam scenario. So now let's look at how we could approach a modulus inequality. So find the range of values of x for which the absolute value or modulus of x minus 4 is greater than or equal to 2. So what we're going to do here is we're going to say, well, I don't know whether that x minus 4 is positive or negative. However, if I square it, it will definitely be positive. So I'm going to square both sides. Remember, when we square an absolute value or modulus sign, we need to square the number. Nothing's going to cancel. It's not like a square root. So we have x squared minus 8x plus 16 is greater than or equal to 4. We now have a quadratic inequality, so I'm bringing everything over to the left-hand side, and we get x squared minus 8x plus 12 is greater than or equal to 0. I can't solve the quadratic inequality. Instead, I solve the corresponding equation and I use my answers to figure out my answer for the inequality. So for 12, we're going to have 6 and 2. So our two answers are x equals 6 and x equals 2. We're not finished. They are not my answers. They're the answers for the equation. So now I'm going to sketch this. It's going to look something like this because there are two positive roots. There's my 2 and there's my 6. My last inequality was greater than or equal to 0, which means we're talking about above the x-axis. So we're talking about this piece and this piece of my graph. That corresponds to these x values and then these x values. So putting those in terms of an inequality, we're talking about where x is greater than or equal to 6, or where x is less than or equal to 2. So let's see a shortcut for this. Now, I'm not as much of a fan of the shortcut of the modulus inequalities. It's very similar to the equations, but a little bit more that you need to remember. So what I'd say is the shortcut is great as long as you remember it, but if you don't think you'll remember it, stick to the longer method. So if we're dealing with x minus 4, the modulus of that being greater than or equal to 2, then maybe x minus 4 was positive and nothing changed. And that will give us x minus 4 is greater than or equal to 2. The other option is that maybe x minus 4 was negative, so it was minus 2. Now, because the sign has changed, the inequality sign will need to change. So this will become a less than or equal to negative 2. So that's really, really important. Because the sign changed, because we're dealing now with a negative, the inequality sign has to change. So now we have some linear inequalities to solve. We solve these the same way as we solve linear equations. We're going to add a 4 to both sides here, and we get x is greater than or equal to 6. Here again, add a 4 to both sides, and we get x is less than or equal to 2. So really nice and simple, but remember, you need to make sure that you fully understand and you'll fully remember this shortcut if you plan to use it. So let's look at an example of a modulus graph and that is linked then to an inequality question. So this uses function notation of f of x and g of x. So the graphs of the function f of x, which is the absolute value of x minus 3, and g of x, which is just 2, is given here. Now, to make life a bit easier for you, I would suggest writing this as y equals 2. Because that's what they have told us it is here. F of x equals the absolute value of x minus 3. You can also write this as g of x equals 2, but g of x, f of x, all of that is the same as y. It now wants us to find the coordinates of A, B, C, and D in this diagram. So where to start? Well, I'm going to start with A and B. Notice that they are both on the line g of x. I've just told you that g of x was y equals 2. So for A and B, we know that the y part equals 2. So all we're missing now is the x part. Let's hold that for a second. Then let's look at C and D. So C is on the x-axis, so that means the y part is 0. D is on the y-axis, which means the x part is 0. So without looking at anything more, then our constant, that straight line of y equals g of x, and our x-axis and y-axis, we've been able to fill in half of each of the points. So now we need to figure out, well, what are the other points? So let's take f of x as x minus 3 and say, well, where is this equal to 0? Now, the good news is if it's equal to 0, then actually the absolute value signs don't matter, because 0 is a neutral number. It's not positive, it's not negative. So that's the same as x minus 3 equals 0. So that gives me x equals 3. So what I've just worked out there was where y equals 0. So that is for point D. So we have, or sorry, for point C. So where y equals 0, so we have 3, 0. Now, for D, let's let x equal 0. So we have the absolute value of x minus 3, but if x is 0, that means it's the absolute value of minus 3, which is 3. Okay, so now we have half of our points done. So we need to look at A and we need to look at B. So A and B both appear where x minus 3 is equal to 2. So we have a modulus equation. I'm going to use the shortcut, which is maybe x minus 3 is 2, or maybe x minus 3 was actually negative 2. And that gives us two answers. So x is 5 or x is 1. Now, which is which? Well, A is here and B is here, which would mean this will have to be 1 and here will have to be 5. So A is 1, 2 and B is 5, 2. It then says, hence or otherwise, solve the inequality x minus 3 is less than, so the absolute value of x minus 3 is less than 2. Now, you can do that using either method we have, squaring both sides, or using the shortcut. However, there's a third method which can only really be used here because they gave us the graph. So we want where x minus 3, which is f of x, is less than 2, which is g of x. So they're asking where is f of x less than g of x. Less means below. So where on the graph are we talking? And we're talking about here. So this is the place where f of x is less than g of x. Now, the corresponding x values for that are all of these here. So that means between, so when x is between 1 and 5, and because it's just a less than symbol, we're going to just use less than symbols. So the answer is x is between 1 and 5. So 1 is less than x is less than 5. Now, like I said, you can use the longer method to work that out and you'll get exactly the same answer. Now let's look at an example of drawing a modulus graph. We're asked, using the same axes and scales, sketch the graphs of the function f of x and g of x. Now, although it says sketch, I'm going to draw these out accurately for practice. So in order to do that, I'll suggest that we use our functions table. So let's start with f of x. Here's what my table would look like. I have values for x. I then use my formula, which is the absolute value of x minus 6. That will give me my y coordinate, and I create a point. Plotting these points, we end up with something that looks like this. So what you'd notice is if we had a normal linear equation, y equals x minus 6, the y-intercept will be minus 6. But since that minus 6 is within the absolute value lines or the modulus lines, this graph cuts the y-axis at a plus 6 instead. Notice that we also hit the x-axis at 6. That isn't a coincidence, it's got to do with the formula of the absolute value of x minus 6. Let's do the same thing for g of x. So here is g of x's table, and here's what it looks like plotted. Now again, g of x is the absolute value of x plus 2. We would expect if it was just y equals x plus 2 to cross the x-axis at y, and the absolute value of 2 is still 2, so it does cross the axis at 2. And notice it touches the x-axis at minus 2. So we get a very similar idea to what we would have between factors and roots. So when x minus 6 is what we have, it is the function within the modulus or absolute value signs, then x equals 6 is where it bounces off that x-axis. Kind of like what we have seen before with factors to roots. For g of x, we have x plus 2 in the absolute value signs. So then when it hits the x-axis, it's going to be at x equals minus 2. So there are some points that would help you to sketch this rather than draw it out accurately. Some other things to note is that the slope of this line is the same as, well, not the same as, it'll be the same numerical slope but with a different sign. So what that means are the two angles that I've just marked, they're the same. So you can think of this as angles, you can think of it as slope. Here, this angle matches this angle. So each of the lines is as slanty as each other, it's just going in a different direction. Remember, this is a reflection. So part 2 asks us to use the graph to solve the inequality the absolute value of x minus 6 is less than the absolute value of x minus 2. Now, first thing I'm going to do is I'm going to label these based on their name. So they're basically asking us, where is f of x less than, I'm going to keep the color coding going, g of x. So remember, less than means below. So where is f of x below g of x? So that happens when the blue line is lower than the green line, which is everywhere here. Okay, so we can see that that starts to happen at 2. So the corresponding x values are along here. So from 2 onwards. So my answer for that will be where x is greater than 2. Part 3 then asks us to verify your answer algebraically. So what we've just worked out, we need to work it out without the graph. So we have the absolute value of x minus 6 is less than the absolute value of x plus 2. It's not suitable to use our shortcut here because they're both in absolute value signs. So we're going to square both sides. So we get x squared minus 12x plus 36 is less than x squared plus 4x plus 4. Let's bring everything over because it's quadratic, but then the x squareds will cancel because I have an x squared on both sides. So then I have minus 12x minus 4x is less than, I'm going to bring my constants over, 4 minus 36. So we get minus 16x is less than minus 32. I am going to change the signs, which will involve changing the inequality. So I'll make a little note, change the sign. So I'm changing the signs, so I change the inequality. So I flipped it. It was a less than, it's now a greater than sign. So I then can divide with no issues, and that gives me x is greater than 2, which is the same answer as we've got before. Question 11. So I'll just state that this is a mock question, so it's a lot more complicated than anything we've ever seen on the paper, but it's a really good one to practice. The graph of the function f of x is the absolute value of 2x minus 3, and we can see that very distinct V shape on the graph below. And g of x is 3 plus 3x minus x squared, and that is a negative quadratic, which again we can see on the graph below. Use your graph to solve where 3 plus 3x minus x squared is less than the absolute value of 2x minus 3. So they're asking us, where is g of x less than f of x? So where is the quadratic lower than the modulus? So that happens here. And when they say lower, we're talking about y values, so higher and lower. So here is a section of the graph that's lower. You can see where the straight line of the modulus is above it. And here is the second piece. Now, I need to just drop a line down to see where we're starting. So it starts at 3 and it starts at 0. So the corresponding x values will be these ones and these ones. So my answer for my graph will be where x is greater than 3 and where x is less than 0. Now that we've used the graph to solve it, part B is asking us to use algebra to solve the same inequality. Now for this, squaring both sides is going to be extremely difficult because we'll be squaring a quadratic, and it's a quadratic trinomial. So what I suggest instead is, in the first instance, flipping it. I like to flip it because I think it's easier to work with the modulus on the left hand side. Once we have that flipped, we're going to apply our shortcut. So the shortcut for modulus inequalities, okay, is that maybe 2x minus 3 was positive, so this stays exactly as is. The other alternative is maybe 2x minus 3 was actually negative, which means the right hand side has to change signs. So these all get a change of signs, but remember, when we change signs, we also then have to change the inequality. So instead of a greater than, it becomes a less than. Now let's solve each of these quadratic inequalities and see what happens. So I'm going to bring everything over to the left hand side here, and I get x squared minus x minus 6 is greater than 0. Turning this to an equation, I get x squared minus x minus 6 equals 0. Factorizing it, I get x minus 3 and x plus 2 equals 0. Solving that, I get x equals 3 and x equals minus 2. We need to do a little bit of a sketch. It is a positive quadratic, and it looks something like this. We have a minus 2 here and a 3. We're dealing with greater than 0, which is above the x-axis. So that means we're dealing with this part and this part of the graph. That means we're dealing with these x values. So my final answer will be x is greater than 3 and x is less than minus 2. So this is my first set of answers. Now let's go to the second inequality we had. So again, I'm going to bring everything over to the left. You can work this slightly differently, but just be really careful with your signs, so positive and negative, but also your inequality signs. So I bring over, it's minus x squared. I bring over minus 3x and I get plus 5x. I bring over minus 3 becomes plus 3, so it's 0. So we end up with this. I'm going to make it positive. So I'm going to change my signs. So x squared minus 5x, which will flip my inequality. Now I make my equation and I solve. It's not a quadratic trinomial. It is quadratic because it has an x squared. We're going to use highest common factor. Don't forget your easy type of factorization. This is actually much simpler than the previous factorization, but often it's a forgotten one with students. Now, so here are my two answers, but they're my equation answers, so I'm going to do a little sketch to figure out what my answers are for the inequality. So I have my 0, or I attempted to go through 0, and 5. We are dealing with greater than 0 again, so it's again above. We're talking about this piece and this piece of the graph, which in turn mean this piece and this piece along the x-axis. This means we have x is greater than 5 and x is less than 0. Now we have 4 answers, but not all 4 are going to be valid. Well, not really even valid, but some of them kind of overwrite others. So if I tell you that I'm over 20 and then I say, well, I'm over 25, the fact that I said over 20 doesn't really make sense anymore because I've given you better information. We'll have something similar with regards to these 4 answers. if we look at what we had for our answer in A, we can use that to help pick out what the correct final answer is. And in this question, that's probably the smartest way to work. However, if we hadn't worked out that answer, let's look at how we would actually work out our final answer. So let's work it visually. What I have here is a number line, and I'm going to use my highlighter. So I'm going to show x is less than -2. So that is here in yellow. And then I have x is greater than 3, which again I'll show in yellow, which is this section here. Now, if I then want to look and figure out, well, the next ones, I'm going to do them above so I'm not overwriting. So x is less than 0 would be all this section here. And then x is greater than 5 is this section here. And remember, these are all going on forever. So which are the best two answers to take? Well, for the negatives, so for the left-hand side, the more complete answer, so it's the green one, will include more, because the green answer of x is less than 0 will also include the answer x is less than 2. So we're not going to include that because it's already included in x is less than 0. On the positive side, it's the opposite way around. It's better for us to work with x is greater than 3 because it already includes the x is greater than 5. So why would I include two answers when I only need to include the x is greater than 3? So my final answer is x is less than 0 and x is greater than 3, which is the same as what we got in the first part.